Let us now look at convex sets. A set C is said to be convex if and only if a line between any two points so the part of the line that lies between any two points also lies in C. So this is different from the definition of the affine set where we required the entire line to lie in the set. Now here we are only requiring the line that is in between those 2 points to lie in the set C. So mathematically we could say that if x1 and x2 are any 2 points in C, then the statement that C is convex is equivalent to saying that theta times x1 plus 1 minus theta times x2 lies in C for all theta that is between 0 and 1, or for all theta in the closed interval 0, 1. So this is another notation for saying that theta is between 0 and 1. So here we have a restriction on theta. Whenever you have a restriction on the parameter that is describing a set, the class of sets becomes more general. So let us ponder over the question as to whether affine sets also convex, or else a related question that whether convex sets are also affine. So to answer this question, remember the fact that in convex sets there is a restriction on theta, while for affine sets there is no such restriction. So which of them is more general? That is the question. Let us consider, for instance, that a set A is affine. So let us say that A is affine, which means that, or this statement is equivalent to saying that if there are 2 points x1, x2 in A, then all points of the form theta x1 plus 1 minus theta x2 also belong to A. Now this is a statement which is true for all theta. So this is true for all theta. Natural implication of this is that this statement is also true for theta between 0 and 1. But this is nothing but the definition of convex sets. For convex sets, we required that for x1, x2 in a set, we required that theta times x1 plus theta times x2 should belong to A for theta between 0 and 1. So in other words, we have concluded from here that given a set A which is affine, it must also be convex because it satisfies the definition of a convex set. If a set is given to be convex, then this statement will be true for theta between 0 and 1, but this statement may not be true for theta outside of 0 and 1. So this means that a set which is convex is not necessarily affine. So the answer to this question is yes, while the answer to the other side is not necessarily. This can also be depicted pictorially. So pictorially you could say that this is a convex set because any 2 points here, the line segment between these 2 points would lie inside the set, right? But this is clearly not an affine set because the points that correspond to theta outside of 0, 1 are actually not necessarily inside the set. They could be outside the set. So therefore, this is not affine, but this is convex. So in other words, all affine sets are also convex. So all affine sets are convex. So convex sets are more general and affine sets are less general. They are a subclass of convex sets. So let us look at several examples of convex sets. The simplest example, we have already seen this, is the affine set. So Ax equal to B. So this is the case. It is already affine, and we have already said that affine sets are convex. So therefore, this is a convex set. Let us take another example, which we have already considered earlier. So set of all x such that ax is less than equal to b. Now this set is actually convex. So how do we show that? If you remember, we needed to check that y equal to theta times x1 plus 1 minus theta times x2, and we needed to check whether ay is less than equal to b, right, for y of this form. In the affine case, we did not put any restriction on theta, but in this case we are saying that theta is between 0 and 1, and x1, x2 are both belonging to C, and this is C. So what is the implication of theta being between 0 and 1? It means that this implies that theta is greater than equal to 0. This is literally written here. And 1 minus theta is greater than equal to 0. This means that when you multiply a with theta x1 plus 1 minus theta x2, you can see that you get theta times ax1 plus 1 minus theta times ax2. Now clearly, since theta is greater than equal to 0 and 1 minus theta is greater than equal to 0, it follows that this quantity is less than equal to theta times b plus 1 minus theta times b, and this is nothing but b. So in other words, we have been able to establish that a times y is less than equal to b. So this whole thing implies that ay is less than equal to b as long as y is of this form, y is equal to theta x1 plus 1 minus theta x2 for theta between 0 and 1. So as long as this condition is true for theta, we have that ay is less than equal to b, which would imply that C is a convex set. So can you give an example of a set which is not convex? A set which is such as this is not convex because a line segment which passes through these 2 points, actually a part of that line segment lies outside the set. So some values of theta which correspond to the line segment between these 2 points provide y values which are outside this set. So this set is not convex. Similarly, you can look at several examples of convex sets in one-dimensional as well. So for example, a set like this is not convex because some part of the line is not included. So sometimes the fact that whether a set is convex or not may not necessarily be obvious, and you may have to manipulate the equations or the set a little bit to find out what kind of set is it. So let's consider this example. X belongs to R plus plus such that log of x is less than equal to 2. Now this notation means that x is strictly positive. X is not 0, it is strictly positive. Now you can see that this set can be written as x between 0 and e raised to the power 2. Right, and from this it is clear that this is a convex set. This is the open interval 0 comma e raised to the power 2. So this is a convex set. In fact, any interval is a convex set, but union of intervals would not be a convex set. So let us take a look at what convex hulls are. To get an intuition about convex hulls, let us take a simple example. So let's say that we are considering a set which contains these 2 lines. Now clearly this set is not convex because you could always select 2 points somewhere such that the line between those 2 points lies outside the set. But what is the convex hull of this 2 set of lines? So the convex hull is the entire region that is between these 2 points. So the entire shaded region shown here is the convex hull formed by these 2 points. So mathematically, the definition can be written as, so convex hull of a set C is given by summation over I from 1 to k theta I xi such that xi belongs to C, summation of theta I equal to 1, and all the theta i's are between 0 and 1. So that is the definition of the convex hull of C. As a simple example, let's take the convex hull of these 2 points. So what is the convex hull of these 2 points? You can see that you can write it as 0 and theta 2, such that theta 1 plus theta 2 equal to 1, and theta 1, theta 2 are between 0 and 1. So what is this set? Since this set is entirely in terms of theta 2, I can just eliminate theta 1 and write it as 0 theta 2 such that theta 2 is between 0 and 1. So this is the line segment which lies between the point 0, 0 and 0, 1. So this part of the line segment is this set. So clearly the convex hull of these 2 points is the line segment that lies between these 2 points. So I hope the concept of convex sets and convex hulls is clear. More importantly, the role that theta plays when specifying convex sets should be clear. And it should be clear that how affine sets are convex sets, but convex sets need not be affine sets.